these lines starting from here all the way down to the bottom. Right now, it's also important to take note that from here, from this group towards the end, these are called the transitional matter. You must know about the different sections. So from here to here, this is known as the transitional matter. Alright, so do they belong to the family of matter? Obviously they are, because they are also called matters, right? It's just that they are called transitional matter. So why are they so special matters? Is because these matters, they don't have group. Did you realize they don't have any group number? Maybe put under this section. Okay, use a different color to highlight. This block from here all the way to here. You can see the red line. See from here to here, these are all the transitional matters. So why don't they have any groups? It's because your valence shell can either be can have a variable numbers. Okay, for example, iron. Okay, your color first. Okay, I'll give you a brief introduction. Okay, look at iron. Iron is found in this section here, which is Fe. Okay, Fe is iron. So this iron, you can have Fe2 plus or Fe3 plus. That means the iron can either choose to lose 2 electrons to form the Fe2 plus ions, or it can also lose 3 electrons to form the Fe3 plus ions. So there's no fixed numbers, just like unlike the other groups of the matter. If you look at group 1 matter, see this group 1 matter, lithium. Now lithium, sodium, potassium, they all have 1 electron on the outer shell, right? Okay, and what does it mean? That it can lose 1 electron. Okay, let's say we have lithium. We draw the structure, 2 and a 3 here, a 2 and a 1 here. It has 1 electron on the outer shell. So you lose that 1 electron in order to form the positive ion, and it forms the lithium plus ion. Right? But then transitional matters is not like that. No. They can actually choose to lose either 2 or 3. They have variable number of electrons that can be lost. That's why it's very difficult to put them in specific groups. Okay, so they don't have any group numbers. Or another example, if you look at the group 2 matters, this group 2 matter, beryllium, magnesium. Okay, let's look at beryllium, Be. It has 4 electrons. So it looks like this, 2, 2. Okay, now you can lose that 2 electrons to form the beryllium ion, like that. But it cannot just lose 1 electron. Right, so it must either lose the number of electrons that it already follows the group number. You get me? Okay, so that's why they are different from the transitional matters. The transitional matters, they can choose to lose their number of electrons on their own. You ask, why? Why do they behave like that? Well, it's just their nature. The nature of the transitional matters is just like that. And because of that nature, they make very, very good matters to be used as catalysts. Right, so you learn about catalysts probably next year. Right, catalysts are referring to substances that are put into the chemical reactions to speed up the rate of the chemical reaction. Right, but they will not take part in the reaction at all. Right, but then the 1, 2, 3 maybe next year then learn, but now just learn about the properties and the pattern of the periodic table first. So far so good. Any questions? Okay, right. So So here we can see that the group 1, group 2 methods will behave very differently from the transition method. Okay, let's talk about reactivity. Do you think they are very reactive? Now, if I talk about reactivity, group 1 and group 2 methods are considered to be the most reactive methods. So now we're going to go into the methods, the concept of methods. Okay, let me go back to the worksheet. All right, so what I've mentioned here are all written over here. Okay, then this point number 6 is where we talk about other trends of the elements in the periodic table. How are they being arranged, or in terms of electronic structure, in terms of the atomic and the ionic radii. Okay, so I'll go through each of them. Okay, now electronic structure is referring to all these numbers, you know, the 286, 284, those are called electronic structure. So we can use the electronic structure to study the patterns of the periodic table. Just like we said, the last digit stands for the number of valence electrons. The number of digits stands for the period, if that means. Okay, so that's the meaning of electronic structure. But what about atomic and ionic radii? Okay, this one sounds a little cheap, but it goes like that. It's very simple. See, periodic table again. Now we agree that the group number starts from 1, 2, 3, 4, 5, 6, and so on and so forth. They stand for the number of shells, electron shells. Do you agree that the size of the atom will get bigger and bigger as the electron shell increases? Right. So that's why as we move down the group, the size of atoms always get bigger and bigger because of the increasing number of electron shells. Make sense or not? Okay. So this is what we meant by atomic radii. Because the atoms are measured by, you know, they are circular, so they are measured in terms of their radius. Make sense? Okay, so that's why moving down the group, the size of atoms always gets bigger. Right, now what about the size of the atoms that goes across the period? So across the period means what? That means if I were to take one of this row, right? If I take one of this row as an example, from lithium to beryllium to the boron, carbon, nitrogen, oxygen, chlorine, and neon, all right? Across the period means from left to right. I see the handwriting becomes bigger. Okay. Sorry, say again. Oh, there is. Just I didn't write it down. And then here, right, actually all these elements, you see all the dashes here, means that they are still under research. I haven't finalized their physical properties like their proton number or the mass number. And then some of these are not found naturally. They are actually man-made. So they are still in the midst of research, haven't finalized the thing yet. Okay. Then you see there are even more. You see all these are man-made. They are all named after the scientists. The one at the bottom here, the Einsteinium, the Californium, Americium. Okay. Yeah. So it depends on how many scientists there are named according to their name. So we don't really have to memorize the periodic table. I can always refer to the periodic table. All right, for more information. Okay, so So across the period, let's say we take the second row, you know what happens to the size of atoms? The size of atoms gets smaller and smaller, right? You may say that the number of shells will stay the same. Like for example, lithium, beryllium, boron, carbon, neon, nitrogen, oxygen, fluorine, they all have 2 shells, right? But why is it that the size gets smaller and smaller as we move across the period from left to right? Okay, the reason why is not in the syllabus. You don't have to learn about that. Okay, but if you are interested to know, let me explain to you. You see, if you look at lithium, beryllium, boron, carbon, neon, and nitrogen, and so on and so forth, what is the only thing that is increasing? Did you realize that the number of electrons increases? Right, and the number of protons also increase. The number of shells never increase, but we're actually adding more and more electrons in the same shell. For example, lithium configuration is 2, 1, beryllium is 2, 2, this is 2, 3, 2, 4, 2, 5, 2, 6. You see the last shell, the number of electrons increases, right? Oh, this is going to be a very big thing because when the number of electrons increases, the nucleus, right, in the atom will keep attracting more and more electrons, causing the overall size to become smaller and smaller. Yeah, the forces of attraction between the nucleus and the valence electrons will get stronger and stronger. Okay, because the nucleus, what is found in the nucleus? What's found in the nucleus? Correct. Okay, protons and neutrons, and then the protons are positively charged, neutrons are neutral, 0 charge. So actually the overall nucleus is positively charged. And then the electrons are negatively charged. Of course, we have forces of attraction, right? Hey, adding more and more electrons across the period, it causes the forces of attraction to be even stronger. So it causes the size of atoms to shrink as we move across the period. Okay, so think on that is the opposite. These are those things to write up, so you all can write it anywhere you are able to remind yourself. But then in the notes, it's already mentioned in the notes. Okay, so that's the atomic radii and the ionic radii. Okay, then bonding and the structure. Bonding and structure. Okay, this is under the chemical bonding topic. Right, chemical bonding topic, which is the next topic after this chapter. Okay, so I'm not sure whether you all learn about covalent and ionic bonding very briefly in the lower secondary. Isn't that? Have sounds just ring a bell, right? What about Tiffany and Kaylee? Maybe teacher mentioned briefly, but didn't really go through the details yet, right? Okay, so if you look at bonding, there are 2 types of bonding. That means the covalent bonding and the ionic bonding. All right, so basically, covalent bonding are the non-metals. You see all these non-metals in this group here? Okay, see all these are the non-metals, right? They can react with one another to form covalent compounds. Okay, then ionic bonding is whereby this group of non-metals react with the metals. And metals react with non-metals. They form ionic compounds. Okay, so take it as it is. Guys haven't learned this chapter, so no need to worry about this point. Eventually, when you move on to chemical bonding, you'll be able to gel all the concepts together. All right. Okay, now melting point and boiling point. Melting point and boiling point. Can you just make a guess? Between the metal and non-metal, which one has a higher melting point and boiling point? What do you think, Tiffany? Metal and non-metal, which one has higher melting point? Here? Non-metal has a higher melting point and boiling point. Good. Okay, then what about Tiffany? Okay, now actually metals are the ones that have higher melting point and boiling point. You think about it, metals are stronger, right? Okay, so why are they so strong? What's got to do with their bonding? So in the next chapter on chemical bonding, we also talk about the bonding in the methods, right? And this bonding in the methods are so strong that it can have, or we can say that it's so strong such that methods usually have melting points that's like above 500 degrees Celsius. Right, like for example, those group 1 methods, sodium has a melting point of 808 degrees Celsius. All right, or if you go down further, the melting point will be higher. Okay, so that's why these are how we deduce the properties of the different elements in the periodic table. Okay, yeah, so let me go back to the notes. Okay, now since we have talked about the methods already, then let's talk about group 1. Now, to answer Kilian's question, actually, this topic is divided into two parts. So okay, it's divided in two parts. The first part is on the group 1 method. The second part is actually the halogen. Now, which is more important? It's actually the halogen is more commonly discussed. The part on the group 1 methods are not heavily discussed in this chapter because we have another separate chapter on methods. Okay. So what do you need to know about the group 1 methods, right? That you must know the name about this is that they are also known as alkaline methods. Okay, they are known as alkaline methods. So why are they called alkaline methods? Oh, there's a reason for it. Because all these methods, such as the lithium, sodium, potassium, refer back to the periodic table, they are so reactive, they can actually react with water to form alkaline. You know what alkaline is like? In secondary 1 and 2, you learn about alkaline. Oh, what are the properties of alkaline? What's the properties of alkaline? Out here? Do you remember what's the property of an alkaline? So P, and then what else? It takes beta, right? pH value. What's the pH value? pH value. pH value. Okay, this is not pH value is about 8 to 14. Right? 7 is neutral, so it's 8 to 14. Okay, so what happened is that all these group 1 methods, when they dissolve in water, H2O, it forms alkaline. Now, alkaline has a formula of this. We call it as hydroxide. Another name for alkaline is known as hydroxide. Okay, hydroxide. Remember in the chapter on the acid and alkaline, in sec 2, we learn about sodium hydroxide, potassium hydroxide, calcium hydroxide. These are all examples of alkaline. Okay, so they are formed in this way. When any of the group 1 method dissolves in the water, they will always form lithium hydroxide, or if I have potassium dissolved in water, it forms potassium hydroxide. Or sodium dissolves in water, it forms sodium hydroxide. Okay, let me balance the equation. So it's so boring to just look at equation. I show you some videos.